Standard DC motors are built for continuous rotation. Hook one up to a power supply, and the shaft spins indefinitely. But in the field of precise robotics, you need a machine to snap to an exact angle and freeze instantly. A basic DC motor lacks the internal logic to do that. It only understands one command: power on or power off. Because it has no way to sense its own position, it cannot hold a specific angle against gravity or an external push. Engineers solve that control problem with servo motors. These rectangular boxes use a splined output gear, typically restricted to a 180-degree physical rotation limit. The 25-kilogram label on the casing measures the motor's torque. At a distance of 1 centimeter from the central shaft, the motor can support 25 kilograms of force. Move out to 2 centimeters, and the leverage drops that capacity to 12.5 kilograms. To hit those torque ratings, the motor needs a specific voltage, usually between 4.8 and 7.2 volts. If a load exceeds these mechanical limits, the motor stalls, causing its current consumption to spike. Turning raw electrical power into exact mechanical positioning requires more than just voltage. The machine must actively process information to determine its location. Inside the servo housing, the primary electrical input wires lead directly to a standard DC motor. On its own, this miniature motor spins too fast and generates too little torque to lift heavy robotic components. A compound gear train solves this. A tiny pinion gear drives a sequence of larger gears, trading speed for force. By the final output gear, a 259 RPM input transforms into a 1 RPM output with massive lifting power. While the gears provide the physical strength, the mechanical system still requires an internal method to dictate exactly when to start and stop. A servo waits for specific, timed bursts of electricity from an external controller, rather than receiving continuous power. This oscilloscope grid tracks pulse width modulation. Every 20 milliseconds, a voltage spike creates expanding and contracting blocks. A wide pulse commands far left rotation. A narrow pulse commands far right. Varying this duration specifies any exact angle. The pulse width functions as a digital coordinate, giving the internal gears a definitive target destination. Knowing the destination is only the first step. The motor must also verify that it has actually reached the coordinate sent by the signal. A potentiometer sits beneath the final output gear, physically rotating alongside the servo's arm. The potentiometer acts as a voltage divider. As the gear turns, resistance changes, scaling the voltage from 5 volts down to 0. A circuit board compares this to the target pulse, driving the motor until any voltage discrepancy is eliminated. This continuous error correction loop defines the closed-loop system, allowing the motor to maintain a precise orientation even when external forces push it out of place. We can map out how human input commands this closed-loop system using a practical breadboard setup. This technical illustration shows the wiring architecture. An external rotary dial connects to an Arduino microcontroller, which sends a signal wire to the servo motor. When you turn the external dial, the Arduino reads that physical rotation as an analog voltage and assigns it a numeric value between 0 and 1023. Software then maps those numbers to a degree scale, translating the 0 to 1023 input into a physical constraint between 0 and 180 degrees. With the target angle calculated, the Arduino fires the corresponding PWM pulse down the signal wire. Because this calculation happens 50 times every second, the physical result is instantaneous. As you turn the dial, the robotic arm mimics the movement and locks into the exact corresponding angle. By combining mechanical torque with electronic feedback, the servo motor acts as a self-correcting mechanism that translates digital logic into controlled physical motion.